Last time we had introduced the notion of a continuous random variable. So this led to the idea of a probability density function, which was a generalization of a mass function to the continuous case. And then we also saw how the CDF connected into this discussion. And just from simple calculus facts, there's a connection between these two as such. And if you use the fundamental theorem of calculus, you could get to something of this sort. So those properties and things like expectation and variance were defined for a general random variable and its resulting density function. Today we're going to take a look at a very specific type of continuous distribution, and it's related and motivated by the Poisson distribution and the Poisson process we talked about earlier. So we will take a look at that here. So this is a new case of a continuous random variable. And so as a little bit of a review, when we talked about the Poisson process, if you had a random variable x in this case, it modeled the number of events that occur. And remember that Poisson process is really used to talk about rare events. So if we were talking about the number of events that occur in a Poisson process, we always need to talk about some sort of rate of occurrence. And the number of events, which is a discrete random variable, could be modeled by a Poisson distribution with lambda times t, where t is some sort of total, and we'll put it as time, but it isn't necessarily time. It could be any sort of equivalent. Now, visually, we could think of the number of occurrences. When we model them with a Poisson process, we essentially space them out in some sort of uniform way. So we would have the first occurrence happening somewhere, the second occurrence, etc., etc., etc. Now, this isn't anything new, and again, it's related to a discrete random variable. But what is going to be new today is that we are going to come up with a probability model for the spacing between those events. And if you think of it in terms of a length or a time, I'm hoping that you can see that it needs to be a continuous variable. So in terms of this picture, we are going to be talking about the spacing. We'll call this with a new random variable. We'll talk about the spacing or the time between events. And this is a continuous random variable. So what we would like to know is, how is this new continuous random variable distributed? To try to answer that question, we have to ask another question. And it goes like this: what is the probability that the first event occurs after some sort of given time, and we'll call this time x, little x in this case. So again, we are trying to model the spacing between the events with a probability model, and we know the number of events can be modeled by a Poisson process, but the spacing needs to be somehow different, but at the same time connected to this. And so to answer that, to make a connection here, we're going to say, what's the probability that the first event occurs after some given time x? So in terms of our probability notation here, we are going to ask, what's the probability that this new random variable, capital Y, occurs for some time greater than x? Why is this the choice? Now, here is the key idea. This question is equivalent to saying that no events happen within a time within the time lambda times x here. Or I should say it's equivalent to saying no events happen within a time x. And that's this key. It's the no events that are important. So now, given that our Poisson process is going to be modeled, in this case, by some lambda x, this is equivalent to the following. Our statement, P of y greater than x, is equivalent to a discrete problem where we say, figure out the probability that x is equal to 0, given that we've got this probability model. And that is a really important connection, because with this connection, what we can do is introduce a mathematical model. So we can use this Poisson PMF. It's a really sneaky way of connecting a continuous probability question to a discrete probability question. And so, according to this Poisson mass function, the probability that we get exactly 0 successes in this time lambda x is just e to the minus lambda x times lambda x to the power of 0 over 0 factorial. And a lot of that stuff simplifies to just e to the minus lambda x. So the answer to our our continuous question comes from a discrete model. Now, this question could be rewritten as the probability that y is rewritten as 1 minus the probability that y is less than or equal to x. And that is another important connection, because this is essentially a restatement of the CDF. This is just the CDF. By definition, this is the CDF of our new random variable y. And so the connection that we can make here is that our random variable has a CDF given by 1 minus e to the lambda, and I'll call it an x. Sorry, I made a mistake here. Shouldn't be a y, it should be an x. And this is 1 minus lambda e to the x. And that is the magic connection that we needed, because we know from basic definition of CDF and PDF that the density function is simply the derivative of this, and it's the x derivative of this expression. So we get negative lambda e to the minus lambda x. And that gives us the connection we need. So we will define a random variable in this form to be following what's called an exponential distribution with a parameter of lambda. And so this is our new statement. This is the new way that we write it. And it will have its density function given by, positive lambda e to the minus lambda x. I just made a sign error up there. And more importantly, f of x is 1 minus e to the minus lambda x. And this is called the exponential distribution. And the main motivation is that this exponential distribution will model the time between events in a Poisson process. And once that's in place, you are able to solve problems involving this. Now, we can show that if we were to integrate this function, we would need to know something about the limits. Our random variable here, we are only ever going to consider times or spacings that are positive. So our random variable is only ever going to be a positive number in this particular case. And so if we need to determine whether or not this is a density, we simply take our PDF and integrate it. And a simple substitution here will show you that this does in fact give you a 1, as expected. The expectation of something that's defined in this case, now I'm switching the letter to a capital X just to be consistent with convention that we normally have. But essentially what we should be doing here is integrating this PDF, lambda e to the minus lambda x, and we'll multiply it by an x. And if you use integration by parts, which everybody loves, you end up getting an answer of 1 over lambda. Even more fun is that if you wanted to calculate the variance of a random variable that's in an exponential distribution, we would have to calculate this difference. This term is easy enough to get from your previous work. This integral, unfortunately, would have to be done by another integration by parts. It's not fun, but it's not difficult. It's just tedious. And what ends up happening is that you get a 1 over lambda squared. So that's all these technical details out of the way. And the point of the story is that we are going to use exponential distributions to solve problems related to time or space, or spacing, I should say, between rare events. So in the next video, we're going to talk about some examples of this.